topic today, conformal Riemannian maps to almost Hermitian manifolds. Nowadays, when you go to the library or the bookstore, when you look at the shelf, you see many books titled with manifolds. So manifolds nowadays in everywhere, because if you need some curved space, you need to consider the manifolds. Nowadays, you see people study statistics on manifolds, manifold learning theory, or differential equations, even some numerical computations. So what is a manifold? Manifold is, more generally, is locally Euclidean spaces. What does it mean? It means if you consider the small neighborhood of a point on the any set, then it will look like the Euclidean space itself. So everything will be smooth, will be flat. But if you consider the global part, then everything will be changed. So like the special relativity and general relativity. Or let's say this way, if you consider the sphere and you consider the one point on the sphere and small...
Bayram.
Yeah.
We see all the first pages, I think.
No, it's okay. So you can see the first page, because I didn't go further, okay?
Okay.
So if you consider the sphere, then one point near neighborhood to that point, it will look like the flat. So manifold, maybe we can think of it this way. Or for unfamiliar colleague, you may think of in this way as a manifold. Think about the surface, not dimension 2, maybe bigger than 2, and not lying, not embedded in the Euclidean space. So it is somewhere, but not embedded in the Euclidean space. But it look like the surface itself. So this is the manifold we consider here. Our manifold is endowed with some measurement. We call the metric Riemannian metric. So our concern is manifolds, maps between them, especially today talk will be in this way. So some maps between these two manifolds. So here my outline, I will start by some basic informations. Then I will try to get my input in this theory. Okay. So one of the main methods to compare two manifolds and transfer the certain structures from a manifold to another manifold is to define the appropriate smooth maps between them. Actually, this is the general idea for the mathematics. When you try to compare the two things, you need to define the maps between them. So in differential geometry or manifold theory, there are mainly two maps. One is called the immersions, the other one is called the submersions. Immersions is the map if the rank of the map is equal to the dimension of the source manifold, is called the immersion. Otherwise, if the rank of the map is equal to the dimension of the target manifold, is called the submersions. If you put the Riemannian metric to manifolds, then these notions called the isometric immersion and Riemannian submersion. So isometric immersion actually is the generalization of the surface theory. Everyone knows the surface. So this is the generalization of these kind of structures. Riemannian submersions we can think of as the generalization of the projection maps. So why we define the Riemannian submersions in the beginning? Because when you need some manifold with some specific curvature, this notion is very useful to consider. So when we consider the two arbitrary Riemannian maps, arbitrary Riemannian manifolds, the above two notions, two maps are very special. Therefore, in 1992, Fisher defined the Riemannian maps between Riemannian manifolds as a generalization of the isometric immersions and Riemannian submersions. So remarkable property of the Riemannian map is that this map satisfies the generalized equal equation. This equation is very important in the geometric optics and physical optics. So in 2010, I considered the generalization of the submanifold defined on the complex manifold. So then I introduced the invariant and anti-invariant Riemannian map. So then I started to generalize the other manifolds. So totally real manifolds, CR submanifolds, and other things. So all these results, I put to one monograph. It's published in 2017 in Elsevier. So this is the book. You can see the update results about the Riemannian maps. Actually, this is the first systematic study of these kind of maps you can see in this monograph. Okay, so now we can mention about the title of this talk. In 2010, in 1992, the Fisher defined this notion. There are two Riemannian manifolds and F between them. And then we say that F is a Riemannian map at the point P1 if the map, the derivative map, transfers the horizontal space isometrically to the range of this map. So it means this satisfies this relation. This G sub n is the metric of the target manifold. Gn is the metric of the source manifold. If this is correct, if this is the valid for every point, then we call this map as a Riemannian map. So you see the picture here. So this black part is transferred to each other, but the other parts remain. So you see this is the generalization of the isometric immersions, because in that case, kernel F star will be 0. Also, it is a generalization of the Riemannian submersions. In that case, the range F star perpendicular will be 0. So, like I said, the isometric immersion, Riemannian submersions are example of these maps. So when we consider the geometrical object, we need to check its geometric properties. So we need a connection derivative to check the change on the subject or on the object on this geometrical object. So that's why we define these two tensors we called O'Neill tensors. This number is connection, Levi-Civita connection, and these tensors have some special properties. T is vertical, A is horizontal, and A measures the integrability of the horizontal distribution. T is the second fundamental of the leaf of this map. By using these two tensors, we obtained these connection relations for these Riemannian maps. Also, if you have map between two Riemannian manifolds, the second fundamental form is defined in this way. Here, nabla F is called the Pohlbeck connection. So this is the vector bundle notion. Okay, so then by using this second fundamental form, we define the harmonic map by putting the conditions, this tension field defined by divergence of the derivative F star will be 0. So you can think of the harmonic map. There are two manifold or two objects, and you try to cover the target manifold by rubber. So this is the generalization of the minimal submanifold test. So that's therefore. Okay, now we define the connection for the mixed terms. So V is a vector field on the vertical or the range F star perpendicular, and X is the part of the tangent part. So we have these conditions and substitute these two relations between them. Okay, now in 2010, I defined as a generalization of this Riemannian map, conformal Riemannian map. So in this case, this is not a conformal map. Pardon me, is not the isometric map, but rather it is a conformal map. So lambda square is a function here. So in this way, we have a conformal map between two Riemannian manifolds. If lambda becomes 1, then we obtain the Riemannian map. So now, how do we define the notions or the geometric object on this map? But first, let me give some examples. The first example is every conformal immersion between Riemannian manifolds is a conformal Riemannian map with kernel F star will be 0. Also, every horizontal conformal submersion is a conformal Riemannian map with a range perpendicular will be 0. Also, like I said before, every Riemannian map also, it is a conformal Riemannian map with lambda equals 1. So you see, these are really generalization of these all maps. But is this useful? So this is the question. So to see this, first we calculated the second fundamental form for this conformal Riemannian map. So we obtained this one. You see, this tells us we can use this idea, this conformal Riemannian map, obtain the harmonicity or the general properties of this map. Remember, the harmonicity or harmonic map is a general notion for the map, not only for immersions, not for only Riemannian submersions or the other specific map. So by using these equation, we can write in this form. Nabla F star. Now, like the submanifold theory, we'll have range F star and range F star perpendicular decomposition. So using this one, we can put in this way. So now we have specific expression of the second fundamental form. Okay, like I said in the introduction, my main input in this theory, after defining this conformal Riemannian map, is to consider the complex manifold. So what we mean by complex manifold? This real manifold furnished with J is an endomorphism, and the square of J is negative identity. Also, the metric is compatible. So it means GM satisfies this equation 1. So if this almost Hermitian manifold is Riemannian manifold J and GM satisfy these conditions, nabla x, j, y is 0 for every vector fields, then we call this one is Kähler manifold. Actually, we can define this Kähler manifold by form, two form. If the two form is closed, because the two form is related to the differential equations, if it will be meaningful to define in this way also. But for our study, this will be enough. Okay, so the invariant and anti-invariant Riemannian map we define in this way. We have a Riemannian map between two manifolds. One is Hermitian manifold, the other one is Riemannian manifold. And if the range F star invariant under these complex structures J and N, then we call this one is if invariant, we call this one is invariant Riemannian map. If like this one is not invariant, is anti-invariant, then we call this map as an anti-invariant Riemannian map. So this one is generalization of the totally real submanifold, anti-invariant submanifold maybe. Okay, so in 2018, we defined with my co-author, actually my former PhD student, Professor Akyol, we defined the conformal anti-invariant Riemannian map. So in this case, we put this F instead of the Riemannian map as a conformal map. Okay, here is the example. Every anti-invariant submanifold and almost Hermitian manifold is a conformal anti-invariant Riemannian map with lambda will be 1 and kernel F star will be 0. Every anti-invariant Riemannian map from a Riemannian manifold to almost Hermitian manifold is also conformal anti-invariant Riemannian map with lambda equals 1. So we can also construct some numerical example. So it shows that there are many examples. Actually, we have some method how to construct the example by using the Riemannian submersions and conformal immersions. So by using this decomposition and the properties of the J, we defined these decompositions B, V, and plus G, C, V. Okay, so how these define or affect the geometry of these map and manifolds themselves? Here is some results. So we can have new criteria for the total geodesic foliation for the range F star. Also, we can have new criteria for total geodesic foliation range F star in this way. So the locally product manifold is important because it appears in many physical modeling. So we can also obtain this locally product manifold criteria in this way by putting some conditions on the second fundamental form and A itself. Okay, now we can also have some new criteria for the harmonic map. So our conformal Riemannian map is harmonic if the fibers are minimal, because fibers behave like the submanifold, and also these two conditions are satisfied. So in case the lambda is vertical, it means it is constant along the horizontal distribution. We call this one horizontally homothetic conformal Riemannian map. And in this case, we have this one. So if F satisfies this one, we have horizontal homothetic conformal Riemannian map. Okay, so for any map between Riemannian manifolds, we call this map as a totally geodesic map if second fundamental form is 0. So what is the geometric meaning of this condition is that it maps every geodesic from the source manifold into the base space. So it maps geodesic to the geodesic. So this is the usual definition for the total geodesic submanifold. Also, it works here. But don't get false idea. So it's not every harmonic map may not be the total geodesic, but every total geodesic map, of course, will be the harmonic map. So also we can find the general total geodesicity of this map itself, putting some conditions in this tool. Okay, so there are more here. So you see these really useful notion for the new results obtained for the arbitrary maps. So you see the umbilical map or umbilical submanifold, umbilical surface are important in the differential geometry and manifold theory. For the differential geometry, we know that every sphere is an umbilical surface. So it is generalization of this notion in this way. So this one is given by the Nora in 19 87. 87. So this weakly G1 umbilical. This one. Here is XY belongs to the source manifold, and G1 is the metric of the source manifold. So if the Z is 0, then we call the G1 is strong umbilical. So in 2000, I think 11, let me show. I show that when you consider this definition, then every G1 umbilical conformal Riemannian map will be automatically total geodesic map. So it means this notion does not work. So we need to define the new notion. Okay. So I define the new notion, and by using this one, actually my notion is this one. So I consider that this is self only for the horizontal vector fields, and this Xi1 will be the tension field of the map itself. So in this way, we obtained this results. The horizontal distribution defines a total geodesic solution on M1. All fibers are totally geodesic, and range F star perpendicular defines totally geodesic solution on M2. Okay. So this give a classification theorem. So if you have a G1 umbilical conformal anti-invariant Riemannian map, you have this one of these one. The horizontal distribution is one-dimensional distribution, or F is totally geodesic conformal Riemannian map. So in this case, the map itself becomes very simple one. Okay, now let me remind the semi-invariant Riemannian map. So this one is the generalization of the CR submanifold defined by Bejanko in 1978. So in this case, we have two subbundles on the range of the these F star. If the one is invariant under these complex structures, the other one is anti-invariant under this complex structure, then we call this map as a semi-invariant Riemannian map. So we carry this definition to the conformal case. So in this case, we just put this map as a conformal Riemannian map. In this case, again, we have this decomposition. Of course, I should note here everything. We define it, range F star, distribution, F itself, everything will be small. Okay? So there is no question to is it defined, or is it possible to define or not. Okay. So examples, this one. Every CR submanifold of almost Hermitian manifold is a conformal semi-invariant Riemannian map with kernel F star 0 and lambda 1. Also, every semi-invariant Riemannian map from Riemannian manifold to an almost Hermitian manifold is a conformal semi-invariant Riemannian map with the dilation will be 1. Also, every conformal anti-invariant Riemannian map from a Riemannian manifold to almost Hermitian manifold is a conformal semi-invariant Riemannian map with D1 as a 0. So if this lambda is not 1, then we call this one is proper conformal semi-invariant Riemannian map. So how to obtain these examples? Because, okay, we defined this notion, but are there many or not? So here is the theorem to obtain the more examples. If you have conformal submersions from Riemannian manifold M1 to Riemannian manifold M2 with square dilation lambda, and F2 as a CR submanifold, CR immersion from Riemannian manifold M2 to do another almost Hermitian manifold M1, M3 with complex structures J, then the composition of these two maps, F2 composite F1, is a conformal semi-invariant Riemannian map with square dilation lambda. So we know there are many CR submanifolds. You can find it in the literature. Also, we know there are many conformal submersions. So this theorem tells us we can find more examples, and there are many examples for the conformal semi-invariant Riemannian map. Okay, by using this method, you can obtain the conformal semi-invariant Riemannian map. Okay, now the geometry of this structure. Again, we defined this decomposition by using the decomposition of the D1 and D2. And then we have these new criteria about the total geodesic foliation of the horizontal distribution D1, also D2, integrability of this D2, and again, the horizontal distribution about the total geodesicity of this distribution, and also for the D2. So why this total geodesicity or the integrability of these distributions are important? Because if you have integrability of this distribution, it means you have a chance, or you have opportunity to do geometry. Otherwise, it will be some linear algebra. But because as a geometer, we want to do geometry, not algebra here. Okay. So this theorem tells that these three conditions, two of them imply the other one. So total geodesicity, horizontal commutative conformal Riemannian map, and some equations about the A and F implies this relation between these three assertions. Okay, so like we check the geometry of the range F star perpendicular as a distribution, and we again check the locally product case. So in this way. Also the total geodesicity and the harmonicity case. You see our equation in the C becomes complicated because we have more geometric object here, and we need to check all the things together. So that's why. So you see the total geodesicity actually reduces to the total geodesicity of the vertical distribution, horizontal distribution, and the mixed terms. So how about the harmonicity? Harmonicity of the conformal semi-invariant Riemannian map is obtained in this form. The fibers are minimal, and these two conditions are satisfied. So it is possible to to convert these conditions by using some forms, but this one it will be more controllable for the harmonicity case. Okay, now I will mention about the conformal slant Riemannian maps, but let me first define the slant Riemannian map. So again, we have Riemannian map from Riemannian manifold to the almost Hermitian manifold. If JF star F, JF star of X between this vector field and the range F star, if this angle between this vector field and this space is constant, then we call this map as a slant Riemannian map. Here, for every P, every point is constant. Also, for every vector field is constant. So this is the definition here. So we carry this definition to the conformal slant Riemannian map. So in this case, again, we consider the conformal Riemannian map instead of the Riemannian map itself, and definition is same. So you see, this is the generalization of the previous conformal Riemannian map. So every slant immersion, so this slant immersion is very well known in literature. Every slant immersion is a conformal slant Riemannian map with kernel f star 0, and the dilation, the function itself, is 1. Also, every invariant Riemannian map from a Riemannian manifold to almost Hermitian manifold is a conformal slant Riemannian map with angle is 0 and the lambda is 1. Also, every anti-invariant Riemannian map from Riemannian manifold to an almost Hermitian manifold is a conformal slant Riemannian map with theta is 90 degrees, pi over 2 radian, and lambda is 1. Every slant Riemannian map is also conformal slant Riemannian map. In this case, lambda will be 1 only. Every conformal anti-invariant Riemannian map is also conformal slant Riemannian map with angle is pi over 2. So if this angle is not 0 or pi over 2 and lambda is not 1, then we call this conformal slant Riemannian map as a proper conformal slant Riemannian map. So again, we have a method how to construct the conformal slant Riemannian map. In this case, we consider conformal submersion from Riemannian manifold to Riemannian manifold, M1, M2. Also, we have slant immersion from Riemannian manifold M2, the complex, actually the almost Hermitian manifold M3. And in this case, if you take the composition of these two maps, then you obtain the conformal slant Riemannian map. So you can see the Chen books. There are many slant submanifold. Actually, I put many examples for this theory also. And then there are conformal submersions. So we have many examples of the conformal slant Riemannian map. Okay, this is the numerical example how to construct the conformal slant Riemannian map. As you see, first we consider the conformal submersion and then the slant immersion in this way. So the resulting composite map is a conformal slant Riemannian map. Okay, now it's time to check the geometry of this conformal slant Riemannian map and the geometry of the distributions. So again, first we have a criteria when any conformal Riemannian map from Riemannian manifold to the almost Hermitian manifold is conformal slant Riemannian map. We can control these criteria by this file. So if this one is satisfied, then our conformal Riemannian map will be slant Riemannian map. And by using this, we obtain these identities between these terms. And for the geometry of the distribution defined on by this map, we have these criteria for totally geodesic foliation case. For the range F star perpendicular, we have this one. So we put these conditions here. Also for the harmonicity and the total geodesicity of this conformal Riemannian map, we have new criteria. In the literature, there are some criteria for the arbitrary maps, but here we obtain new criteria by using this notion. Okay, now for the harmonic map, we have these criteria by using this slant angle theta and the decomposition of these range F star perpendicular. Okay. So these are the basic maybe theory we update with my student, former PhD students, Mehmet Akif Akyol. I like to thank him for my collaboration. So after that, there are many papers, but I just put the recent papers here. So you see there are many open problems here to study. These papers are published in 2022 and 2023. The first one is related to the quaternion scalar manifolds, and the second one is give the new condition for the conformal slant Riemannian map, and this one is the third one, obtain the conformal anti-invariant Riemannian maps for the contact manifolds. Contact manifolds are also important class of the manifold theory. Complex manifolds are always even dimensional. The contact manifolds are always odd dimensional. So the one is, you can think about the even dimensional prototype. The other one is odd dimensional prototype. And the fourth one is by putting the Solitin condition here. So these colleagues study this conformal Riemannian map by considering the Yamame Solitin for the on the total manifold. Also, like these colleagues study the conformal point bus slant Riemannian maps. Remember, I stressed the definition. Okay, let me show you again. Okay, one more. Yeah. So like I said here, this angle is constant for every point belongs to M1, also for every vector field. Okay. So in this case, we call the conformal slant Riemannian map. So in this paper, okay, the first one, in this paper, these colleagues consider the conformal slant Riemannian map, but it is the tangent, the angle itself is a function. Okay, so it is independent from the vector fields, but it is dependent on the point itself. So every point you have, you obtain something else as a number. But in our case, everywhere, for every point, every vector field, we have same constant number. But here, it changed from point to point. So you see, this is the generalization of the conformal slant Riemannian maps. Also, these are my former PhD students, and now they are professors. So they use this notion, obtain the new result by using this one. And the conformal slant Riemannian maps with totally umbilical fibers. This one is very important. These dear colleagues obtain the nice results about this kind of conformal slant Riemannian maps. Okay, so you see, there are many studies going on, and I believe will be more near future. Okay, so here some my references. You see these Akyol and me together, we published basic results on this theory. And then, okay, this is the classical monograph, harmonic morphism between Riemannian manifolds. Actually, we use this, we obtain the many new results for the harmonic maps. So these are the Chen book, Geometry of the Slant Submanifolds. For the interested, colleagues, they may look this book to find more examples for the slant submanifolds, slant immersions. You see, by using these slant immersions, we obtained many new examples for the conformal slant Riemannian maps. So you can get idea from that. Okay. So here I like to point some maybe open problems. You see for the Riemannian maps, we consider these inequalities, Kasuraki inequalities for the Riemannian maps between Riemannian manifolds. So one can consider this case for the conformal Riemannian maps. Okay. Okay, I leave here. Thank you for listening me.